Hi dear students, so let us discuss the angular momentum in case of the rotation about a fixed axis. So pictorial representation is given. So here the z axis is the axis of the rotation of the particle p. You can see the omega is the angular velocity, v is the linear velocity of the particle, and r is the position vector of the particle p. The two components of r are there, that is one it is cp, that is the perpendicular component or perpendicular distance of the particle p from the center of mass c, and another one it is the vertical, that is oc. So in vector addition, vector summation, if we are considering, vector r is equal to vector oc plus vector cp. Okay, so you know that if we want to find out the angular momentum of the particle p at the point or here, the angular momentum L is equal to r cross omega, sorry, r cross p. L is equal to r cross p. Now this r is having the components OC and CP. Here if you are considering only one particle or the ith particle, then Li will be is equal to Ri cross Pa. As well, if you want to find out the n number of particles are there, then if you want to find out the angular momentum of the n number of particles, you have to do the summation. Then the total angular momentum L is equal to summation of I is equal to 1 to n Ri cross Pi. Okay. Now you can see here this r perpendicular component is on the or upon the plane of the circle or the path. Okay, r perpendicular to your is upon the plane, but OC it is perpendicular to the plane. OC it is perpendicular to the plane. So now as you have to consider the r value, two components are perpendicular and OC are there. Okay, so considering them, you can find out the angular momentum at this point in such a way. Angular momentum L is equal to, that is R is equal to OP, that is OC plus CP, then P is equal to MV, then the equation L is equal to Ri cross Pi will become OC cross MV plus CP cross MV. Okay, OC cross MV plus CP cross MV, that is R is equal to OC plus MV CP, then P, OC cross P, P is equal to M into V, mass into velocity. So OC cross MV plus CP cross MV is actually the angular momentum value L. Now consider this CP cross MV. CP is actually lying along the path or on the plane of the path, on the plane of the rotation, the CP it is lying. So CP cross MV as you are taking, that is CP and V, both are in the same plane. The product, cross product of them will be in the direction of the axis. Okay, in the direction of the axis of the rotation. So that is the direction of the axis of rotation, it is z axis. So the unit vector which will represent that axis will be k cap. So the CP cross MV will become R perpendicular MV. That is actually the magnitude R perpendicular MV into K cap. Now we will rewrite the V as omega R perpendicular. The linear momentum will be is equal to R omega. That relation you have to use here. That is V is equal to omega R perpendicular. Then the CP cross MV will become, that is, M R square perpendicular omega K cap. Where actually this is in the direction of the axis, that is in the Z axis, and the unit vector is K cap. So we will write this angular momentum value as LZ. Okay, LZ. Now, so LZ value is mr square perpendicular omega into K cap. Now consider the total angular momentum. Okay, so we have considered the component angular momentum, that is the one portion of the angular momentum value, that is Cp cross Mv we have found. Now the total angular momentum L will be equal to this Lz plus the OC cross Mv. OC cross Mv. Okay. So the angular momentum value total will be summation of Li. Suppose if we are considering n number of particles generally, so total angular momentum summation of Li is equal to summation of Liz. Liz is actually this one, the Cp cross Mv term, plus OCI cross Mi Va. So here this Lz and L perpendicular things are the components of the angular momentum L. Now let us come to the L perpendicular. L perpendicular is actually summation of OCI cross Mi Va. When the cross product OCI cross Mi Va as you are taking, the angular momentum vector will be perpendicular to the axis of the rotation. So as we are considering a rigid body with a fixed axis of rotation, we have to neglect the perpendicular component of the angular momentum, as we have done in the case of the torque values and all. Okay. So the perpendicular component of the angular momentum, that is summation of OCI cross Mi Va, that is L perpendicular, will be considered as 0. That is L perpendicular will become 0. Then this equation, that is total angular momentum L, will become Lz, and that will be equal to I omega K cap. So rigid bodies which are symmetric about the axis of rotation, the axis of rotation is one of their symmetry axis. Suppose if the axis of rotation is one of the symmetry axis. Okay. So for such bodies, every particle which has velocity Vi, there exists an, in the opposite side there exists an particle which is having a minus Vi velocity. So they will cancel each other, their velocities will cancel each other, and as a result the angular momentum value for the perpendicular component will always be 0. Now, so Lz value we have seen. So Lz is equal to I omega K cap. Now we have to find the d by dt of Lz. That is rate of change of the angular momentum with respect to time. So rate of change of angular momentum with respect to time. So taking the differentiation on both sides, that is d by dt of Lz is equal to d by dt of I omega k cap. Okay, so here I is a constant, taking I outside, and omega d omega by dt is actually the angular acceleration alpha. So the equation will become dl by dt. We know that rate of change of angular momentum will be the torque value, that is a linear momentum. Rate of change of dp by dt is equal to f. So same way dl by dt will be is equal to tau, and tau is equal to I into d omega by dt, that is tau is equal to I alpha. So you can consider that is f is equal to ma with tau is equal to I alpha. So you can see tau is actually the torque. Torque is actually the analog of force in the angular motion as well. I and m, alpha and a. So this is the Newton's second laws of motions analog for the rotational motion, that is tau is equal to I into alpha. Okay, so dl by dt is equal to, or dl divided by dt is equal to torque, and the torque value is equal to I alpha. Okay, now let us come to the conservation of angular momentum. So in the case of the conservation of angular momentum, same as there in the case of the conservation of linear momentum, here if the external torque acting upon a particular body is 0, if there is no external force acting, then the angular momentum value will be conserved or constant. That is, if tau is equal to 0, we have already seen dl by dt is equal to tau. If tau value is 0, then L will be constant, and the L can be rewritten as, that is d by dt of I into omega. So L is equal to I omega. Okay, L is equal to I omega. That means L constant means I omega, I into omega will be a constant. Okay, so in such a conserved motion, that means if there is no external torque acting upon a particular body, then I omega will be a constant. That means if the inertia increases, to make the product of I and omega constant, omega will decreases as well. If the inertia decreases, to make this one as a constant, the omega increases. Okay. With a representation, it is explained in your textbook, that is a girl on a chair. Whenever the girl is rotating in the chair, and whenever she is stretching the hands, what will happen? As she stretches the hands, the moment of inertia value increases, and as a result the omega value decreases. And as well, whenever she means unstretching the hands, that means whenever she keep the hands close to her body, means inertia will decreases, and as a result the angular momentum omega will increases. Okay, so here we will neglect the frictional force. Okay, the frictional force we will neglect, otherwise the torque value will be there. For removing the torque value, we will be neglecting the frictional force. Okay.